Hello, this is the luckiest maths teacher in the world. Your life is about to change again because we're going to learn about experimental probability. So, first thing that I want students to be able to do is I want you to understand the difference between theoretical and experimental probability. Now, last video we went through theoretical probability, and remember I said that's what should happen. So we looked at the probability of getting a head on a coin. I know it's really simple. We figured out it was a half. And what that meant was that we expect that if we toss the coin many times, we would get half heads and half tails, because each probability is a half. But we also said that that's not what always happens. If you toss a coin, say 4 times, you might not get 2 heads and 2 tails. You might get all heads. So, experimental probability is what actually happens, and that's what we're concerned with today. So we're talking about experiments when we do something over and over again. So we can think of tossing a coin, rolling a die, picking a card out of a deck as experiments. And we want to see what actually happened. What was the proportion of the time a certain event happened? So we're using a formula that's only slightly different. So this formula up here. So remember, the formula for theoretical probability was the number of ways it can occur over the total number of outcomes. So this one's only slightly different. It's the number of times something happens over the total number of trials. So if you toss a coin 5 times and get 3 heads, then the experimental probability would be 3 over 5, okay? So that's the difference between them. Now I'm going to actually go through a bit more formally how to calculate the experimental probability. Okay, so let's say I do toss a coin, and I'm going to put the results up here of tossing that coin about 5 times. So I get heads, tails, heads again, another heads, and yet another head. So I've tossed the coin 5 times, and I've got 4 heads. So remember the way we usually write probability, we write P, and then in brackets the probability we're actually finding, so in this case heads. So the experimental probability of getting a heads, so the number of times the event occurs, so it occurred 4 times, I got 4 heads, and the total number of trials, how many times I did the experiment, is 5. So the experimental probability of getting a heads in this case was 4 over 5. Of course, if you toss 5 coins, you might get a different answer. You might get 5 tails or whatever. But this is just the probability of heads in this particular experiment that I just did for you in front of your eyes. So probability of heads is 4 over 5. Now note that this is actually quite a bit larger than the theoretical probability. Now the theoretical probability of getting heads is still a half. This coin still has half or 50% chance, half probability of landing on heads each time I toss it. It's just in this case I happen to get more heads, okay? So the theoretical probability does not need to equal the experimental probability, okay? Just because the experimental probability is 4 over 5 doesn't mean the theoretical probability is 4 over 5. Just because the theoretical probability is a half doesn't mean the experimental probability will be a half. So even though we're talking about the same event, i.e. getting heads on a coin, the experimental probability is the proportion of heads I actually got. The theoretical probability is the proportion of heads I thought I would get, a half, okay? So they do not equal each other, okay? So another example, let's say I rolled a die a few times. So first time I got a 1, roll it again, and then I got a 2, then I got a 1, then I got 2 again, and then I got 5. Okay, so in this case of rolling the die, the probability, the experimental probability of getting, say, a 1 is 2 over 5. Okay, because it happened twice. I got 1, 2 rolls where I only rolled 1, and there were 5 rolls in total. The probability of getting a 6 in this case is 0. because I didn't actually get any 6s. Or in other words, it's a 0 divided by 5, which is 0. Okay? So again, the theoretical probability of getting a 6 is not 0. It's not impossible to get a 6 when you roll a die. I'm sure you've all done it before. It's just that in this particular case, I didn't actually get any. So the experimental probability is 0. Now, in this case, it would be actually impossible for me to get an experimental probability of 1/6, because even though that's the theoretical probability, I only rolled the die 5 times. And 1/6 of 5 is not a whole number. And I can only get a whole number of 6s, or a whole number of 1s, or a whole number of 2s. I can't get half a 6 when I roll a die, okay? So, experimental probability, easy to calculate, but the thing that brings people undone is they sometimes equate it with theoretical probability. They're different, and we've just seen why. All right, now we're going to do one more thing. We're going to solve a problem using this. All right, so the last thing I want you to be able to do is use experimental probability to solve problems, okay? So here's the problem. I actually used these spinners, each of these spinners, 20 times, and I recorded how many times I landed on red, how many times I landed on yellow, blue, and green. And I recorded the results down below here. So in trial A, I landed on red 5 times, blue on 5 times, yellow on 6 times, green on 4 times, and so on. I want you to figure out which of these 3 trials, A, B, and C, goes with which of these spinners, 1, 2, and 3. And we're going to use our principles of experimental probability. Okay, so let's look at the first trial, A. So we're looking down here, okay? So I got 5 red, 5 blue, 6 yellow, 4 green. So I got a fairly even number of times that I landed on each of these colours, right? So the experimental probabilities of these 4 colours is very similar, okay? So I'd be looking for a spinner where the distribution, the area devoted to each of these colours is approximately equal. In other words, I'm looking for a spinner whose theoretical probability for red, blue, green, and yellow is very close to being equal, because that's what happened in my experiment, okay? So I expect that that's what the theoretical probability might be. If I look here at B, so I got no red, no green, but I got a lot of blue, and I got quite a few yellow as well. So I'd be looking for a spinner that has a very small, if any, red area and a very small, if any, green area, because they were very unlikely to come up. I got blue 14 times, so its experimental probability is 14 out of 20, 14 over 20, or 0.7. So I'd be looking for a spinner that has quite a large, more than half of its area blue. This one over here, so the experimental probability of red, I'm just going to do it for this example so it doesn't take too long. So the experimental probability for red is 8 over 20, and hopefully you can all simplify that nice and easy to 2 over 5. For blue, it's 7 over 20. And hopefully you can see 7 over 20 is very close to 1/3. For yellow, it's 2 over 20, which is 1/10. And for green, it's 3 over 20, which is also 0.15. So I'm going to look for a spinner that has theoretical probabilities as close as possible to these. Now, it doesn't have to equal this. I don't have to find a spinner where the experimental probability is exactly 2 over 5 for red, okay? I don't have to look for a spinner whose theoretical probability of blue is exactly 7 over 20. I just want something close, okay? Now, if we look over here at the third spinner, we can see that blue has a theoretical probability of 2 out of 6, or 1/3. Red has, similarly, a theoretical probability of 1/3. For green and yellow, it's 1/6. Now, what we know is that one over 10 is close to a sixth. 0.1 is close to 0.16 recurring. 3 over 20, which is 0.15, is very close. So these two are close, so are these two. 2 over 5 is close to a third. 7 over 20 is very close to a third. So that's why I conclude that 3 is trial C. So trial C used spinner 3. If we go back, so for B, it's clearly spinner 1, because in that case, I had an experimental probability of 0 for red and green, and you can see on the spinner here, there is no red, no green, so the theoretical probability is also 0. We can also see that the theoretical probability of getting blue is very high. It's more than a half, because the area of the circle, because more than half of the circle is blue, and we can see that there is also a chance, not a great chance, but a chance of getting yellow. So that's why I conclude that trial B used spinner 1, and of course that means that trial A used spinner 2, and that's makes sense because in spinner 2 the theoretical probability of red, yellow, blue and green is exactly equal. The experimental probability is not quite equal, but it's close to equal, because as I said, experimental probability does not need to equal theoretical probability, okay? Sometimes it does, but more often than not, it doesn't. Okay, so throughout this video, we should be able to understand the difference between experimental probability and theoretical probability. We should be able to calculate experimental probability, and we should be able to use this to solve problems, and I hope you can do all that. Otherwise, have a wonderful day. This has been the luckiest maths teacher in the world.